Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. In this video we'll talk about dot product, and as a motivation let's recall that when working with vectors we have some operations to do on vectors, and the basic operations are addition and subtraction, how to add and subtract vectors, and the third operation was scalar multiplication, that is how to multiply a vector by a scalar or a number. Here there is another operation in vector, which is multiplying vectors themselves, and for that there are two operations really, or two ways to multiply vectors. One is called the dot product and the other is called the cross product. In this video we'll concentrate on dot product. So here we'll discuss this operation of multiplying vectors, the operation known as the dot product, and we'll see, or we'll discuss some of its properties or applications. So let's start with the definition of the dot product. So the definition: let U and V be two vectors in a 3 space. The dot product of U and V, the two vectors U and V, denoted by U dot V, is defined as follows: U dot V equals U1 V1 plus U2 V2 plus U3 V3. So it is the sum of the product of the corresponding components, U1 V1 plus U2 V2 plus U3 V3. So this is the definition of the dot product, and the first observation about the dot product of these two vectors is that the answer, the result, is a number or a scalar. So when you find the dot product of two vectors, we get a real number. Let's consider one example here, given the vector U and the vector V with the corresponding components. The dot product U dot V is computed as follows. You just multiply the corresponding components. 1 times minus 1 plus 2 times 4 plus 3 times 0. You simplify and add. This is minus 1 plus 8 plus 0, and the answer is 7. So the dot product of these two vectors is the number 7. This is how we dot product two vectors. It is a very simple operations. Now we discuss some of its properties. In fact, and the properties are really similar to the properties of real numbers. Okay. Properties of the dot product. So let U, V, and W be 3 vectors in a 3 space, and let K be a scalar. The first property, the dot product is commutative. So U dot V equals V dot U, the commutative property. The second property is the distribution property. Dot product distributes over addition. U dot V plus W equals U dot V plus U dot W. The dot product of any vector with the 0 vector, whose components are all 0, is the 0 number. Notice how we write the 0 vector and the 0 number. We distinguish them by just putting an arrow. An arrow over the 0 means it is the 0 vector. A 0 without an arrow, it means just the 0 number. Now multiplying a real number by the dot product. You can take the constant or the scalar K into the vector U or into the vector V. So this equals KU dot V or U dot KVU. The last property is the dot product of a vector by itself is equal to the magnitude of the vector square. So just to illustrate, the proof is very simple. You just take any 3 vectors and just try to find each side, and then see that the 2 sides are equal. And for that, let me just prove the number 5, because it is a nice property and very important when we work with vectors. Proof of 5. How to prove 5? We take a vector U in 3 space, which is U1, U2, and U3, and find the dot product. Now the dot product of U with itself by definition equals U1 times U1 plus U2 times U2 plus U3 times U3. And this equals just U1 squared plus U2 squared plus U3 squared. And really this is nothing but this is just the square root of U1 squared plus U2 squared plus U3 squared, all squared. But the square root is just the magnitude of the vector u. So this is just the magnitude of the vector u, which is the square root, power. So this is the proof. So u dot itself is just the magnitude square. Now we consider one of the main applications of the dot product, which is in determining the angle between two vectors. So for that, let's first define the angle between two vectors. So let u and v be two non-zero vectors in 3 space having the same initial point. So for example, so these are the two vectors, u and v, and they have the same initial point here. Then what is the angle between them? The angle between the two vectors is the angle theta, determined by the two vectors that satisfies the condition. Theta has to be between 0 and pi. Basically the smaller one. So here the angle here will be between u and v will be considered this one, theta. Will not take the outer one. The outer one will not satisfy this condition, 0 to pi. So take the smaller one, okay. So the angle will be that one. It has to be between 0 and pi. Another possibility here, if you have the vector here, u, and v here, the angle theta between the two vectors is this angle, theta. It satisfies the condition 0 to pi. We will not take the outer one. The outer one is larger than pi. We take always the smaller one. Okay. If we take, for example, these two vectors, this is u and this is v. Again, the angle, well, either you have this one or the outer one. We take the smaller, the one satisfying this condition, and this will be this angle here, theta. So this is the definition of the angle between two vectors. It has to satisfy the condition theta between 0 and pi. This is the definition. Now the dot product will help us find the angle between two vectors. And for that we have the following theorem. Let u and v be two non-zero vectors, and let theta be the angle between them, between them. Then now the relation between the dot product and theta is given as follows: u dot v equals magnitude of the vector u, times the magnitude of the vector v, times the angle between them, cosine theta. So this is the relation between the dot product and theta, the angle between the two vectors. This theorem follows from really the law of cosines that we usually study in orientation or Math 002. Okay. Now we can use the theorem here just to define some terminology regarding the reposition of two vectors u and v, and we say the following definition here. Definition: two non-zero vectors are said to be orthogonal or perpendicular perpendicular. So we use these two terms, orthogonal or perpendicular. If the angle between them is pi over 2 or 90 degrees. In fact, with this definition and this theorem, we can have the following test. So theorem here, two vectors are orthogonal if and only if their dot product is 0. Two non-zero vectors. And this is obvious from the theorem here. Notice if they are orthogonal, if the angle between them is pi over 2, then cosine pi over 2 is 0, so this side is 0, so the dot product is 0. Now if the dot product is 0, since the two vectors u and v are not 0, this one is not 0, this one is not 0. Cosine theta equal to 0 implies theta equals pi over 2. Okay. So this is a test. This is a test to decide the orthogonality of two non-zero vectors. Just a note now here, if one of the vectors is zeros, in fact the zero vector is perpendicular to any vector. So this is why we assume it is non-zero. We assume in this theorem that the two vectors are non-zeros. Now we consider the notion of the direction angles and the direction cosines of a vector in 3 space. So if we have a vector in 3 space, we need to know or to define the direction angles of u. In fact, the angle between the vector u and the standard unit vectors I, j, and k. These angles are called the direction angles of u. So here the angle between the vector u and the vector I is alpha. The angle between the vector u and the vector j, we call it beta. The angle between the vector u and the vector k we call it gamma. So the direction angles of the vector u are alpha, beta, and gamma. The angle between u and I, the angle between u and j, the angle between u and k. So this is the definition of the direction angles of u. The direction cosines of the vector u are the cosine of these angles. So they are cosine alpha, cosine beta, cosine gamma. So these 3 numbers are called the direction cosines. Well, it is very natural to just know how to find the angles alpha, beta, and gamma. And this is what we use the dot product. So here for cosine alpha equals the vector u dot the vector I over magnitude of u, magnitude of I. This is by using the relation between the dot product and the cosine of the angle between them. Okay. I have u dot I is 1, 0, 0. So we have u1, u2, u3, 1, 0, 0. When you dot them, you get just u1 over magnitude of u. Magnitude of I is 1. It is the unit standard vector. Okay. Similarly for cosine beta, it is u dot j over magnitude of u times magnitude of j. When you do the dot product, I get u2 over magnitude of u. And cosine gamma, similarly, cosine gamma, it is u dot k over magnitude of u, magnitude of k, and this is U3 over magnitude of U. From this we can solve for alpha and beta and gamma to get the corresponding direction angles. There is one property between these, some properties, we write in a theorem here, theorem. If alpha, beta and gamma are the direction angles of the vector U of U1, U2 and U3, then in fact cosine squared alpha plus cosine squared beta plus cosine squared gamma equals 1. So the sum of the squares of the cosines will give you 1. And this is very, very, very obvious. In fact, just apply the definition of cosine alpha, cosine beta, cosine gamma. So this is just a quick proof. Cosine squared alpha plus cosine squared beta plus cosine squared gamma equals, you just square each term. So this is U1 squared over magnitude of U squared plus U2 squared over magnitude of U squared, U3 squared over magnitude of U squared. And this is just U1 squared plus U2 squared plus U3 squared over magnitude of U squared. But what is the magnitude of U squared? It is just U1 squared plus U2 squared plus U3 squared over itself, U1 squared plus U2 squared plus U3 squared, and this is just 1. So this is the relation between the direction cosines of a vector. Further, we have the following in fact property here. In fact, for any vector theorem here, or another property, for the vector U1, U2, U3, we can write it in terms of the direction cosines. In fact, we have U equals magnitude of U times the vector cosine alpha, cosine beta, cosine gamma. The vector whose components are the direction cosines. Again, the proof. You have the vector U equals U1, U2, and U3. What is U1, U2, U3 in terms of the direction cosines? From the definition here, cosine alpha, cosine beta, cosine gamma. Notice U1 equals cosine alpha times the magnitude of U. So this is just magnitude of U cosine alpha. The same thing for the second two, U2, magnitude of U cosine beta. The last one, magnitude of U cosine gamma. Now if you take the magnitude of U as a common factor, you get the result. Magnitude of U times cosine alpha, cosine beta, cosine gamma. So this is how to write any vector in terms of the direction cosines. Now we consider the notion of vector projections. And the situation is as follows. We have two vectors, U and V, and we have the angle theta between them. Vector projection is as follows really. Well, we do the following. We take a perpendicular line from the vector U onto the vector V, or onto the line containing the vector V. So when you take a perpendicular line from the vector U onto the vector V, we get this line, and we get this angle here, 90 degrees, and we get this line segment here. This line segment, we think of it as a vector here, so let me call it W. this vector's W is called really the projection of U on V. So this is projection of U onto V. The notation for this one is as follows: projection of U onto V. Our objective is to find the vector W, or the projection. To find a vector, you need two things: the magnitude and the direction. So here, from the given picture here, what is the magnitude of W? Magnitude of W. Using this right angle triangle, we notice that really that the magnitude of W, well, if you find cosine theta, magnitude of W over magnitude of U. So magnitude of W equals magnitude of U cosine theta. Also, what is the direction of W? Direction of W. Okay. In fact, according to this picture, it is the direction of W is the same as the direction of V. So the same as the direction of V, direction of the vector V, direction. Now, from a previous work, we have for the magnitude for the vector W, it is equal its magnitude times a unit vector in the direction of W, This is how to write any vector, okay, in terms of its magnitude and direction. For the magnitude of W, which is absolute value of U, times cosine theta. So this is for the magnitude. A unit vector in the direction of W. W and V are in the same direction. So we can take the unit vector of V, So we write V over the magnitude of V. So this is the unit vector in the direction of W. So this is W. Using the properties of the dot product, we can rewrite this in a different way. Remember here, if I have vector a magnitude of V, then I will have the dot product of U and V. So just multiply and divide by the magnitude of V. So when you multiply, you get the following. So magnitude of U, magnitude of V, cosine theta, times the vector V over magnitude of V squared, because I multiplied and divide by magnitude of V. So I have magnitude of V squared. Now this becomes the following. This is the dot product, U dot V. V over the magnitude of V squared, which can also be written as follows. So this is U dot V. This is a real number. The denominator is a real number. I can pull the real number outside, away from the vector. So this is magnitude of V squared. So this is just a scalar or a real number times V. So the vector W is just a multiple of the vector V. And this one, W, is good. We call it, this is just a projection of U onto V. So this is the definition of the projection of a vector on another vector. So it is, and it's always the projection on V, so it is in the direction of V, a multiple of V. The dot product over the magnitude of V squared, There is another quantity related to this, which is really the magnitude or the signed magnitude. This quantity, in general, is called the component of U into V. So here we have also another quantity here, the component or scalar component of U onto V as the notation comb for component, comb of U on V, and it is equals this magnitude of U cosine theta. Again, in terms of the dot product, I can write this in terms of the dot product as follows. Just multiply by magnitude of V over magnitude of V. So this equals magnitude of U, magnitude of V, cosine theta over magnitude of V. So this becomes U dot V over magnitude of V. So this is the component of U onto V. So this is the second one. Of course, needless to say, in this process, we are assuming that the vectors U and V are non-zero. U and V are non-zero vectors. Consider the first example here. Find the angle between the vectors U and V. For the angle, we use, this is an application of the dot product. So we have the following. We have the formula U dot V equals magnitude of U, magnitude of V, cosine theta, where theta is the angle between the two vectors U and V. We have the vector U and we have the vector V, so we can find the dot product, the magnitude of U, the magnitude of V. Then we end up with one equation in theta. So just find the dot product now. The dot product 2 times 1 plus minus 1 times 1 minus 1 times 1 plus 1 times 2, 1 times 2. The magnitude of U is root 2 squared 4 plus minus 1 squared 1 plus 1 squared 1 times the magnitude of V. So this is again square root of 1 squared 1, 1 squared 1, 2 squared 4. Cosine theta. Simplify, so this is 2, 4 minus 1. This gives us 3. And this is root 6 times root 6 cosine theta, or 3 equals 6 cosine theta. This implies that cosine theta equals 3 over 6, which is just half. Okay. So we need to find theta. So this implies theta equals, of course, remember, we have to remember that the angle has to be between 0 and pi. So what is the angle whose cosine is half and lying in this interval? It is just pi over 3. So this is the angle between the two vectors. We consider the second example. Find the dot product of the two vectors U and V if the magnitude of U is 2, the magnitude of V is 5, and the angle between the two vectors U and V is pi over 4. Here, how to know the dot product if you know the magnitudes and the angle. Again, we have one formula relating the dot product and the angle, which is the following formula. U dot V equals magnitude of U, magnitude of V, cosine theta, where theta is the angle between U and V. Now it is obvious, you have the magnitude, and you have theta. So everything is available with us. Just substitute to get what is required, the dot product. So here magnitude of u is given 2, magnitude of v is 5, and cosine pi over 4. So this is just 10, cosine pi over 4, 1 over root 2. And this is when you just multiply by the conjugate root 2, you get 5 root 2. So this is the value of the dot product. We consider this a problem here. Find all values of k so that the vectors u with components k, 2, 3 and the vector v with components minus 1, 3k, 4 are orthogonal. So we need to find k so that the two vectors are orthogonal. Well, how to decide whether two vectors are orthogonal? Well, it depends on the dot product. Two vectors are orthogonal if and only if their dot product is 0. But here u, the vector u, is perpendicular or orthogonal to the vector v if and only if the dot product is 0. So we try to find the dot product and then solve for k. So this implies just compute the dot product. So this is just, what is the dot product? Just multiply the corresponding components. K times minus 1, this is minus k, plus 2 times 3k, which is 2 times 3k, plus 3 times 4, 3 times 4, equal to 0. Simplify, so this implies this is minus k plus 6k plus 12 equal to 0, and this is just 5k equals minus 12, and hence k equals minus 12 over 5. So the two vectors are orthogonal or perpendicular if the value of k is minus 12 over 5. This is the solution. That's it. We consider the following problem. Find the direction cosines of the vector u with components minus 3, 0 and 2. Here you have a formula for the direction cosines. We just apply these formulas. We have the formula here, cosine alpha equals u1 over magnitude of u, and cosine beta equals u2 over magnitude of u, and cosine gamma equals u3 over magnitude of u. What is the magnitude of u? The magnitude of u equals root u1 squared plus u2 squared plus u3 squared equals magnitude. So this is u1, this is u2, this is u3. When you square them, you get 9 plus 0 plus 4, which is root 13. So now apply, just substitute. So this is u1 is minus 3 over the magnitude, which is root 13. u2 is 0 over the magnitude, which is root 13. And this is just 0. And u3 is 2 over the magnitude, which is root 13. So these are the direction cosines, cosine alpha, cosine beta, cosine gamma. If we want to find the direction angles, i.e. if we want to find alpha, beta and gamma, then we have to solve for alpha, beta and gamma. So here alpha equals cosine inverse of this quantity, beta cosine inverse of 0, gamma cosine inverse of 2 over root 13. Usually in this case, we need to use a calculator. This is the answer. We consider now the following problem. Show that the magnitude of u plus v squared equals magnitude of the vector u plus 2 times the dot product of u and v plus magnitude of v squared. Here to show this, of course, U and V are any two vectors in a 3 space. To show this, we use the properties of the dot product. And one of the properties is given as follows. So, U dot U equals magnitude of U squared. So this is the key property that will be used to solve this problem. So here we apply this. So we start from the right hand, the left hand side. So this is U plus V squared. By this property, it is the dot product of U plus V with itself. So this is U plus V dot U plus V. Now we multiply, and we notice one of the main properties of dot product is the vectors behave like real numbers when it comes to the dot product. So you can multiply term by term. You use the distributive property. So multiply U by the two vectors plus V by the two vectors. U dot U, so this gives you the U dot U plus U dot V plus U dot V. Now you do the same thing with V. V dot each of these. V dot U, V dot U plus V dot V, V dot V. Really, using the dot product between vector, it is like multiplying polynomials, okay? But always keep the order, the vectors in their orders. Now, this is U dot U plus U dot V. Here, U dot V and V dot U. Again, the dot product is commutative. So U dot V equals V dot U. So I can replace V dot U with U dot V. U dot V. Because the dot product is commutative. Plus V dot V. Now, what is U dot itself? This is the key property. Magnitude of U squared. Magnitude of U squared. Plus U dot V plus U dot V. It is just twice U dot V. Plus V dot itself, again using the key property, it is the magnitude of V squared. And this is the right hand side. And this is how to show the given identity. We consider now the following problem. Show that if the vector U is orthogonal to the vectors V1 and V2, then the vector U is also orthogonal to the sum V1 and V2. So let's see what is given here. What is given in the problem? Given. We have U is orthogonal to V1. This is, and U is orthogonal to V2. So these are the given information. The vector U is orthogonal to V1 and V2. What is wanted here? Wanted. Show the vector U is orthogonal to the sum V1 plus V2. This is what is required. Well, how to show that two vectors are orthogonal? Well, two vectors are orthogonal if the dot product is 0. So to show this, I have to show that U dot the sum equal to 0. i.e., so this implies the same thing as show U dot V1 plus V2 equal to 0. If we show this, then we'll conclude that the vector U is orthogonal to V1 plus V2. Well, how to show this? Well, just try to compute this one. Now here, well, U dot V1 plus V2. Using the properties of the data product, you can just multiply, just like multiplying polynomials or multiplying numbers. U dot V, U dot V1 plus U dot V2, U dot V2. Now what is U dot V1? Well, here we use what is given. We are given that U dot V1, U and V1 are orthogonal. Well, if they are orthogonal, this means what? U dot V1 equal to 0. So this equals U dot V1 is 0 plus. What about U dot V2? Again, we are given that vectors U and V2 are orthogonal. Then the dot product U dot V2 equal to 0. So U dot V2 equal to 0. Now 0 plus 0 is 0. So U dot the sum equal to 0. Then the conclusion, so U, the vector U, is orthogonal to V1 plus V2. And this is the end of the solution. Consider now the following example. Let U and V be the given vectors in the 3 space. The first part here, find the projection of the vector U into the vector V. Here we need to apply the formula, direct application of the formula. So we have to memorize the formula. So solution here, we need the projection of the vector U onto the vector V. And this is by the formula, it is U dot V over the magnitude of V square. So this is just a scalar times the vector V. Remember, always the projection on V is really parallel to V. So just find these quantities, U dot V and the magnitude of V square, and then just simplify. So here we have the following. So here just say U dot V equals. So just multiply the corresponding components. 1 times 4, this is 4, plus 5 times 1, this is 5, plus minus 3 times 2, which is minus 6. 4 plus 5 minus 6, this is 9 minus 6, and this is 3. This is for the data product. Now I need the magnitude of V square. So what is the magnitude of V? This is root 4 square, which is 16, plus 1 square, which is 1, plus 2 square, which is 4. And this is root 21. So this gives us the magnitude of V square. It is just 21. Okay. Now substitute in the formula. So this gives us the following projection of U into V equals, the data product is 3, the magnitude square is 21. The vector V, what is the vector V? The vector V is 4, 1, 2. 4, 1 and 2. Simplify, this is just 1 over 7, and this is 4, 1 and 2. Multiply through with the vector 4 over 7, 1 over 7, and 2 over 7. This is the vector projection of U onto V. The second part of the question, find the scalar component of U onto V. Again, you have to just remember the formula. So the solution here, we need the component of U onto V, and this is just the data product U dot V over the magnitude of V, We already calculated the data product of U and V, which is 3, so this is just 3, over the magnitude is just root 21. So this is the scalar component of U onto V. The third part of this equation, find the projection of V onto U. V onto U. Notice here we switch between U and V. So again, you have to use the formula, but switch the formula between U and V. So this is the original formula, U onto V. If you switch, you just replace each U with V. Okay. So projection, the formula here, projection, so solution here, projection of V onto U, this equals V dot U over magnitude of U squared. The projection is parallel to the vector U times U. So this is the formula, which is really the original when we switch between the rules of U and V. Now compute U dot V and magnitude of U squared times U. Well, U dot V or V dot U is already calculated, which is 3. So I will put 3 here. The magnitude of U squared, magnitude of U, I have here 1 plus 5 plus 25 plus 9, 1 plus 25, 1 plus 25 plus 9. So this is the number here. Okay. Times the vector U, which is the following, which is 1, 5 minus 3. 1, 5, 1, 5 minus 3. Okay. Simplify. So this is 3 over 35. 1, 5 minus 3. We can keep it like, we can keep the answer like this, or just you can multiply. So this gives us the following: 3 over 35. 3 over, when you multiply by 5, you get 3 over 7. And this is minus 9 over 35. So this is the projection vector, or the vector projection of V onto U. That's it. Let's consider now the following example. So let V be the vectors given by 4, 0, minus 3. Find a vector U such that the scalar component of U onto V equals 2. So we need to find a vector U. So let me call this vector U, just U1, U2, and U3. I need to find this vector U so that the component equals 2. So I have now the component of U onto V equals 2. V is known, so what is missing is U. What is missing here is U. So here we use the formula for the component of U on V. So here, component of U onto V, it is the dot product of U and V over the magnitude of V. And substitute. So this implies the component is given as 2. The magnitude of V, just find the magnitude of V. So this is root 4 squared, which is 16, plus 0, plus 9, plus 9. U dot V, find the dot product of U and V. So U1 times 4, so this is 4 U1, plus 0 times U2, plus 0 times U2, plus U3 times 3, minus 3, so this is really minus 3 U3. Simplify, so this is just 2. The denominator is root 25, 5, and this is 4 U1 minus 3 U3. So this implies 10 equals 4 U1 minus 3 U3. Now we end up with one equation, and two unknowns. So it has infinitely many solutions. Since the question asks about one vector, a vector, I can just find one solution. And to find one solution, it is very simple. You can choose any value for u1 and solve for u3. For example, if I choose u1 to be, for example, 1, then I get 10 equals 4 times 1, which is 4, minus 3 u3. And this implies 3 u3 equals 4 minus 10, which is minus 6. And hence u3 equals minus 2. So with u1 equals 1, I get u2 equals minus 3. So what is the vector? So the vector u1, u2, u3. Well, I can. u1 is 1. u3 is minus 2. What about u2? Well, there are infinitely many possible values of u2. Since I need only one vector, I can choose any value here. For here, I can choose just, for example, 1 or 0 or 2 or minus 3. Let me take, for example, just 1. So this is one vector. If I need other vectors, I can choose 1, 2, minus 2. A third vector, 1, 10, minus 10. A fourth vector, 1, minus 100, minus 2. So there are really infinitely many vectors satisfying the conditions of the problem. But we need only one. So this is one possible solution.